In this lecture video, we begin our look at random variables and distributions. Now, a random variable is a function or mapping from the sample space of an experiment to the set of real numbers. Mathematically, this is represented in the following way, where x is the random variable, s is the sample space of the experiment under consideration, and then we're mapping to R, which is the set of real numbers. Now, the complete set of values taken on by the random variable x is called the sample space of x, and will be denoted by script A or by A sub x if the context requires explicitly identifying in the notation the random variable of which it is the sample space. Now, this may be advantageous, for example, when sample spaces of more than one random variable are under consideration. Mathematically, the sample space of x is defined in the following way. So script A, the sample space of x, is the set of all values taken on by the random variable as E, which is the elementary event, varies across the sample space of the original experiment. Now, we consider two types of random variables: discrete random variables and continuous random variables. A discrete random variable is a random variable possessing a finite or countably infinite sample space. A continuous random variable is a random variable that can take on any value in one or more intervals on the real line. So we're classifying random variables according to the nature of their sample spaces. Now let's first consider discrete random variables and their distributions, and in particular we're going to talk about probability mass functions right now. So let x be a discrete random variable with sample space script A. So what that means is that script A, the sample space of x, is either finite or countably infinite. In other words, it's a discrete set. Now suppose that there exists a function, which we'll denote by lowercase f, that satisfies the following three conditions. First, the function is always non-negative. At every point at which we evaluate that function, it always returns a value that is greater than or equal to 0. In addition, when we add up the values taken on by that function f over all values of x in the sample space of the random variable x, then that sum is equal to 1. And then for any subset of the sample space, in other words, for any event involving the random variable x, we can determine that probability by adding up the values taken on by this function as x ranges over the values in that particular event. Now, if those three conditions are satisfied, then this function f is called a probability mass function, or PMF, of the discrete random variable x. So this PMF, this probability mass function, gives us the probabilities associated with the random variable x. Now, in addition to the probability mass function, there is another function that is related to the distribution of a random variable x. It's called the cumulative distribution function. The cumulative distribution function, or the CDF, of a random variable gives the probability that the random variable takes on a value less than or equal to each value on the real line. In other words, the CDF gives us this kind of a probability right here in the middle of slide 161. For a particular value of x on the number line, and notice that this is a lowercase x, then the CDF gives us the probability that the random variable x takes on a value less than or equal to this specified value, little x. Now, the domain of the CDF of a distribution is the entire real line. What that means is that the CDF is defined at every point on the real line. Now, some properties of the CDF function are listed on the following slide. So let f be the CDF of some random variable. Then the CDF f is a non-decreasing function. If we think of a graph of the CDF, then as we go to the right, it's either going to go up or it's going to remain constant. It will never go down as we go to the right. In addition, the CDF is right continuous. The probability that x takes on a particular value of little x is given by the value of the CDF evaluated at that little x minus the limit of the CDF evaluated at y as y approaches little x from below. The limit of the CDF as x goes to minus infinity is 0, and the limit of the CDF as x goes to positive infinity is 1. Now let x be a discrete random variable with sample space script A and PMF little f. Now, one common convention that is used in statistics and that I will be using in this course is the following. If we use a particular letter, a lowercase letter, for the PMF of a discrete random variable, then we're going to use the uppercase version of that letter to represent the CDF for that distribution. So if x is a discrete random variable with sample space script A and PMF little f, then the CDF of x, which we're again going to denote by capital F, is defined at every real number little x, and it's equal to the probability that the random variable x is less than or equal to the specified value little x, and this is obtained by evaluating the PMF at all values of what we'll call k in the sample space that are less than or equal to the specified value of x. So in other words, the CDF is defined this way, and for a discrete random variable, we obtain this probability by adding up the values of the PMF corresponding to the values of k that are less than or equal to the specified value of x, which is the point at which we want to evaluate the CDF. So let's look at some examples. Let's first consider the experiment of flipping two fair coins. So let's flip two fair coins, say a quarter and a nickel. So these are distinguishable coins, by the way. For example, a quarter and a nickel. And we're assuming here that they're fair. And then when we do this, let's record the up faces. Then let's let the random variable x be the number of heads obtained. So we want to determine the sample space of x, we want to find the PMF of x and graph it, and we also want to find the CDF of x and graph the CDF. Now, we've already looked at this particular example of flipping two fair coins, and when we looked at it, we found that the sample space of the underlying experiment has 4 outcomes: heads, 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 tails, tails, heads, and tails, tails. So for example, the first letter corresponds to the outcome on a quarter, and the second letter corresponds to the outcome on the nickel. And so we have these 4 outcomes. Then the random variable x is a function that maps from the sample space to the set of real numbers in the following way. The random variable evaluated at the elementary event heads, heads is equal to 2. The random variable evaluated at the elementary event heads, tails is 1. The random variable maps the elementary event tails, heads to 1. And then the random variable maps the elementary event tails, tails to 0. Now we can see that there are 3 distinct values taken on by the random variable x. And so the sample space of x, which again we're going to denote by script A to distinguish it from the sample space of the underlying experiment, which you'll recall is denoted by cap S. So the sample space of x consists of the 3 values, 0, 1, and 2. So indeed, let me go back here, x is mapping the sample space of the underlying experiment to a subset of the real line. Now, how do we determine the probabilities of x? And at what points do we determine these probabilities? Well, we have to make sure that we determine the probability associated with each of the elementary events in the sample space of x. So for every value of x in script A. And so the probability that x is equal to 0 is equal to the probability of the event tails tails. And because these are, the two coins are fair, if we go back to the and look at the sample space of the underlying experiment, if the two coins are fair, then that implies, by the independence of the coins and the fairness of the coins, that these four elementary events are equally likely. And so to calculate the probability of some event involving these events, all we have to do is count the number of ways that the event can occur and then divide by 4. And so there's only one way for x to equal to 0. That's if we get the outcome tails tails, and that probability is 1/4. On the other hand, the probability that x is equal to 1 is equal to the probability of the event heads tails or tails heads, and that event has a probability of 2/4. And then finally, the probability that x is equal to 2 is equal to the probability of the event heads heads, and that event has a probability of 1/4. So putting that all together, we can write down the PMF, construct the PMF of x, and this is the way that we would do it for a discrete random variable. Right? For each value of x in the sample space, which I've got listed right here, I specified the corresponding probabilities. So the PMF of x is equal to 1/4 if we evaluate it at x equal to 0. It's equal to 2/4 if we evaluate it at x equal to 1, and it's equal to 1/4 if we evaluate it at x equal to 2. And again, what do these probabilities represent? Well, remember that the PMF is giving us the probability that the random variable x is equal to the specified value, okay, in the argument. Now, remember that the PMF has to be defined at every real number on the real line. And so for values outside of the sample space of x, the PMF is going to be equal to 0. It's going to evaluate to 0. So for any other value of x, all right, the PMF will be equal to 0. So so this last thing we've done here, this is a very important component of this PMF to be sure to include. When we do that, the PMF is defined at every real number. And I would point out that in particular, the PMF is strictly positive at every point in the sample space of x and 0 at any point not in the sample space. And that's always good to remember. When we're dealing with discrete random variables, the PMF for that random variable will be strictly positive for every value in the sample space of that discrete random variable, but it will be 0 everywhere else. Now, what does the graph of the PMF look like? Well, it's going to look like a histogram, and so this is what it looks like here. So we see that we have a rectangle corresponding to each of the values in the sample space of x. And the area, well, let me back up a second. Each of those rectangles is centered over the value that it corresponds to. The area of that rectangle is equal to the probability associated with the value over which it's centered. So the area of this rectangle here, centered over 0, this corresponds to the probability that x is equal to 0, and so that area is 0.25, as is indicated in the notation or the number, the value above that rectangle. And then the area of this rectangle centered over 1 is equal to 0.5, and the area of the rectangle centered over 2 is 0.25. Now, I would also point out that the total area of all three rectangles is 1. And that's always going to be the case because remember, because f is a PMF, the probabilities always add up to 1. All right, then we have the CDF, the cumulative distribution function. Now remember that the CDF, which we're going to in this case denote by cap f, is by definition the probability that the random variable x takes on a value that is less than or equal to whatever is specified there in the argument of the CDF. So we've got little x there as the argument of the CDF, and that is the same as the value of little x right there that I'm pointing to. And we can think of the cumulative distribution function as a probability accumulator. As we march down the real line, we are accumulating probability at various points. And in this case, when you think of it this way, and when you derive the or evaluate the value of the CDF, then this is what you get. Again, it's a piecewise defined function that is defined at every point on the real line. Now, if we evaluate the CDF at any value of x that is less than 0, to the left of 0, how much probability have we accumulated at that point x? Well, because we don't start accumulating probability until we get to x equal to 0, we've not accumulated any probability yet. So that's why the CDF evaluates to 0 at any value of x that is to the left of 0. Once we get to 0, and in particular if x is any value greater than or equal to 0, but strictly less than 1, then we've evaluated that probability of 1/4 that is associated with x equal to 0. Once we get to 1, but as long as we're strictly, as we're to the left of 2, then we've not only accumulated the 1/4 over that associated with this probability, but we've accumulated the 0.5 here. So the total accumulated probability at that point is 0.75 or 3/4. So the CDF evaluates to 3/4 for any value of x that is greater than or equal to greater than or equal to 1, but strictly less than 2. And then once we get to 2, we've accumulated all of the probability that there is, and so the CDF is going to evaluate to 1. Now, what does the graph of this CDF-F look like? Well, we'll show you a graph in a minute, but let's think about a few things here about the CDF, just pointing these things out again. So it is defined at every value of x on the real line. And you can see, based on what we've come up with here, that it's a non-decreasing function. It's equal to 0 at every point to the left of the smallest point in the sample space of the random variable. For every value of x less than or equal to 0, 0 being the smallest value in the sample space of x, the CDF evaluates to 0. The CDF is equal to 1 at every point at or to the right of the largest value in the sample space, which again, let's see, the largest value in the sample space was 2, and the CDF evaluates to 1 at every value of x that is greater than or equal to 2. So those are some useful things to consider and to remember about the CDF. And so here is what a graph of this CDF looks like. You can see that it's a step function. It's going to be 0 for every value to the left of 0. It's going to be 1. I'm sorry, not 1. It's going to be 0.25 at every value of x at or to the right of 0, but strictly to the left of 1. And then once we get to 1, it's going to jump up to 0.75, and it'll remain there until we get to 2, at which point it becomes equal to 1. And then as we go out here to positive infinity, keep going to the right, all the way up to positive infinity, it remains there at 1. If we think about going here to the left, out to minus infinity, it's going to stay there at 0. So that's what the CDF of this random variable looks like. So this is a good place to stop this particular video. We'll pick up the next example in the next lecture video.